and our first section or our first unit done. I've got two things for you. The most prominent one and obvious one you're probably curious about is your exam. So I threw out the exams here before class, hopefully to save some time, and it looks like I think it did. It looks like you guys were able to grab them and have them in front of you. If you didn't get it, you might want to come get it now. They're laid out here in alphabetical order here, and you can grab those. Because what I want to do then is jump really quickly into looking at the test and the results here of the test, or at least some of the problems in case there were some you missed. Certainly, for the most part, I can say, you can have one of those if you want one. Yep. Yeah. Yep. Yeah. That's okay. Good. Where was I here? What I was saying is certainly you guys got the right idea, and scores were excellent, to say the least. There were some common errors made along the way. I thought I would address those. How come I'm not getting this to come up here? What am I doing wrong here? Video. Go input detect in S video. There we go. And anyways, so like I said, let me jump into doing some of these problems and see where you are. You're looking for your test? Right over here, alphabetical order, right there. Okay. And then we'll jump right back into Chapter 5, because what I really want to get to now this week is examples from Chapter 5. I think you'll see Chapter 5 really go up a notch, a significant notch from what you saw in Chapter 4. But hopefully, since you guys did so incredibly well in the first test, it won't even faze you. You'll just go, it won't even challenge you. You're obviously ready for the challenge. Let's look at number 1 here real quick together. Number 1 was probably the one that if there was a mistake on the test, you made it here. People overlooked the obvious. At least I hope it was just an overlook and not you did it wrong here. But clearly this one does not have a constant acceleration here. So be very careful, okay? Most of you saw right through it, but a few of you were like, oh, I'll just use the equations for constant acceleration for this one that doesn't have constant acceleration. So that could easily have been your mistake. And so if it was, make note of it. Don't do it again on the final exam here, okay? But here is a rocket car, and it says here in number 1 that it has an acceleration. The acceleration is 5 plus 4t. So clearly an acceleration that changes with time. So any of those constant kinematic equations do not use, okay? You need to go back to the fundamental idea that velocity then becomes the integration of acceleration with respect to time. So if you put in your acceleration, your acceleration equation, you will get a 5t plus a 4t squared over 2, which reduces to 5t plus 2t squared. And so that would be step 1. And many of you saw right away then that you needed to know the time that it took to get to a speed of 500. You will need that in a second. So setting that equal to 500 and solving for time comes out to be two different numbers, one a negative, one a positive. I'll grab the positive one, and so you should have about 14.6 seconds. And so there's step 1. How much time did it take to get to a speed of 500? And poor choice on my part. That's obviously an unrealistic, even for a rocket car here, speed. I don't think any rocket car has gone quite that fast yet. But anyways, that's, unfortunately, a number I picked a little too high when I was writing the problem. But if you saw that and got the 14 seconds, then you probably saw part 2, which was then now integrated again to get position. And so integrate velocity a second time, And since we've already got velocity there, when we integrate it a second time, we will get a 5t squared over 2 plus a 2t cubed over 3 plus, oh, and I should have mentioned a constant of integration here. My bad, trying to go here a little quick so we can get into chapter 5. But there was a constant, don't forget it. And those of you who did it, I could tell you didn't forget it, but you stopped, you looked at it, you pondered it, you said, what is that constant? It's the initial velocity. The problem clearly says start from rest, so you set it equal to 0 and moved on. So, and that's what I did here. And then likewise here, setting this equal to 0 or initial doesn't really matter because it's how far did it travel, so you would want to be subtracting this anyways. But then you can get your x minus your x naught if you call that initial, but then it's your 14.6 seconds squared and your 2/3 times again that 14.6 seconds. So that's why, if you didn't catch it, and you may not realize you need the time until you've actually done this step, but once you do this step, you realize you can get position if you know time, and you can get time from velocity. So that was obvious the problem, and that was obviously the problem all the way through. I think the first 4 were really kind of the same thing, again and again and again and again. It is use this dimension or this motion to get one thing, use it to substitute back into the other. And so you guys obviously saw it very well. And so this comes out to be 2609 meters for how far it went. And so there was number 1. Again, clearly a one-dimensional motion and clearly a 2-step parts with it. Jumping into number 2, again, another one-dimensional motion. The first one hopefully being the easier of the 2. Here we have as it says, a careless hiker falls into a pit. It's 10 meters deep and trying to draw attention to himself because he injured his voice box when he falls down. So silly story, but nonetheless needed something there. We're going to throw the object up. And in this case, the first part of it says, if you throw the rock up at 15 or 17 meters per second, how much time does the rock spend in the air? So straight up, straight down, one-dimensional motion, or obviously from chapter 2. The picture there looks something like this. The rock goes up, rock comes back down. And so hopefully you started off with an equation involving distance and time and acceleration. But in this case, we do have a constant acceleration. So you can use that set of equations that are valid only for constant acceleration. So you have them. And then this one, mathematically, is the easier one of the 2, and even conceptually is the easier one of the 2, although part B didn't seem to really throw anybody off. There's a lot of different ways you can get part B. But you notice right away that, hey, you're going to go, the final position is 0, and your initial position is 0. At least that is one option. If you put your coordinate system down here at the bottom of the pit, then your initial position is 0. You don't have to do that, and some of you chose not to. That was fine. I wasn't, and as I said in class, there's not just one way to do these problems, and I'm not requiring you to do one way, but I am going to look at your logic, and I'm going to grade it based on the logic. Are you self-consistent? Where did you put your origin? Many of you put the origin down at the bottom, and I did too when I worked out the solutions. Kind of made sense. You called up positive, so this became a 17t, and you called down negative, and of course the acceleration is at 9.8. So you would have had to have known all that, which you clearly did. And now you solve this for time, and clearly there's 2 answers. The first one is t equals to 0, and the other one then comes out to be 3.47 seconds. And so there's the time in the air. And again, not the only way to do it. I think it's the shortest and most consistent way, but maybe I'm even wrong there. Some of you took 2 or 3 steps, so I didn't mark anything wrong. But don't miss the easy step here. Don't miss the obvious. You don't have to calculate how much time does it take to get to here, and then figure out how much time it takes to get to there, and then figure out how much time it takes to get down to there, and then figure out how much time it takes to get all the way there, and add them all together. That's not necessary. This can be done in one swoop. It's one equation, one constant acceleration the whole time. Some of you did one that wasn't so bad. You just calculate how much time did it take to get to the top and then doubled it, and okay, that seems to be logically sound. But this works just as well. In fact, I think it helps you set up B, because again, there are many ways of doing B, but I think one of the easiest ways is just say, well, if I start at position 0, how much time does it take to get to position 10? And just set it equal to 10. I mean, that's what you're asking. You're asking, okay, when is it at 10? And it doesn't surprise you if there's going to be two answers. There's going to be a time when it's going up, and there's going to be a time when it is coming down. So you have a quadratic equation, and you solve this for time, you will get 2 times. You will get 0.75 seconds for one of the times, and you will get 0.272 for the other time. And if you give this some thought, what it means then is the difference between those two must be the time that it was above the 10. So just subtract the 2. So 2.72 minus 0.75 coming in to be 1.97 seconds. So there's probably the shortest way. I don't know if that's the shortest way, but it does involve a little bit of interpretation. In fact, any of the approaches you take are going to have to involve some kind of interpretation of what you mean by the numbers. And so that's probably like I said, what I think is the best way of doing the problem. Why did I minus them? Okay, so before I subtract them, let's stop. What do they mean? What does this mean? Now, this is the time, in this case there's 2 answers, that the object is at 10 meters. So when is the object at 2 meters? 10 meters. Thank you. Well, when I throw it up, it's at 10 meters. On its way up, then it gets to its highest point, and it comes back down, it's at 10 meters again. So there should be 2 moments in time when it is at 10 meters. Fair enough? Sure enough, that's why I got 2 answers. So this and this are the 2 times it is at 10 meters. The question asks, how much time is it above the ground level? All right, so at 0.75 it got above ground level, and it remained above ground level until 2.75. So the difference between those must be how much it was above ground level. And so that's why I subtracted. Find out what that time difference is. And of course there are many other ways of doing it, and I knew there was a lot of ways when I set up the problem. I did not realize how many there were until I started grading it and going, oh, okay, I see where they're going. Oh, hey, and I see that. Oh, I didn't see this, and so I was like, wow, a lot of creative approaches there. So a lot of you took different ways of how much time did it take to get to the top, subtracting, dropping it, all kinds of ones that were certainly valid, maybe longer and maybe missing some simple things like this. So I wanted to make sure you saw it, but certainly still valid. Number 3, here's the kick of a football. Again, it's a projectile motion. Again, it's constant acceleration. And so, again, most of you saw right into this really well. So that tells me you're ready with Chapter 4. You're ready to go on here to Chapter 5 and jump right in. Probably the only thing that may be a little bit of work is I threw in some English units just to make you transfer or to do some unit conversion, the kind of stuff we did back in Chapter 1. So the first part of this tells us that we're 90 feet away. And so you have a choice here to make. Are you going to convert everything into feet, or are you going to convert everything into meters? It's clearly your choice. But what you know is the acceleration is 9.8 meters. So you either need to convert that into feet or this into meters. Most of you decided to convert into meters. Made sense. I did too. So I'll go that direction. And when you do that, you can do your substitution. In place of feet, we can put 12 inches. In place of inches, we can put 2.54 centimeters. In place of centimeters, we could put times 10 to the minus 2. So there's our substitution of our unit conversion. Replace a foot with 12 inches, replace an inch with 2.54 centimeters, replace a C for centa with times 10 to the negative 2. So when you multiply all this out, you come up with 27.4 meters. So there's the distance, not a very far distance, and yet they still miss. So I hope this isn't a professional kicker here, because this would be sad. Here is the height they've got to clear the crossbar, 10 feet. Same idea, you can start with 10 feet, but again, in place of feet, put 12 inches. Again, instead of inches, put 2.54 centimeters. And again, instead of centa, put times 10 to the minus 2. So again, just do our substitution, treating our numbers and our units, you know, the same mathematical properties. So after we go 10 times 12 times, we get 305 meters. So there is the height that we need to be when we get to that distance, and we need to make it clear. So there's a little thought process going on in here, and it looks like you guys saw, most of you saw it. For those of you who didn't, let me show you here. You want to know essentially how high is it when it goes this far, right? If it goes further than that, fine, or how far it goes, doesn't really matter. Some of you did those calculations, and that's fine, but we don't really know or care about how far this football is ultimately going to go. What we do care about is when it does get to this distance, will it be above or below that point? Of course, that's not even counting left or right. Most field goals are even missed left to right, not to the distance here. But there's our question. So if we jump to the horizontal distance, we can say x equals initial x times initial velocity in the x direction times time plus 1/2 acceleration in the x direction squared. And if we put in our numbers here, we can say, okay, what we're trying to do is we're trying to see how much time will elapse for this thing to go 27.4 meters. We will call the kicking point 0. Again, you don't have to. I think all of you did. It kind of makes sense. There's our origin. And so you're going to start off at your position 0. And the speed that you kick it is 17 meters per second. But we need to multiply it by that cosine of 52 degrees. Again, another big thing I was looking for, but I don't recall anybody missing that. So you saw, right, you know, that's what you do. You don't just put the 17. I think there actually was one or two at 17. So if you need the horizontal speed. It's not just the 17. It's 17 cosine of 52 degrees multiplied by time. And since it is, again, a projectile here with nothing horizontal, no horizontal acceleration, then we can put a 0 there. And so if you then set this equal or solve this for time, it comes out to be 2.62 seconds. So there's the time it takes to go that distance. And so now, once we know that, we can come over and solve for the vertical motion. And putting in our time, we can then see, well, how high is it at that point? So again, taking the kicking point as the origin at 0, we can put in a 17 sine 52 degrees, and then the time of 2.62 seconds, then the negative 9.8, and then half of that gives me the 4.9, and the 2.62 seconds squared. And if you put those numbers in, you get 1.46 meters. And it's still in the air, but lower than the crossbar. And so this is what I was looking for. I know I did kind of say in parentheses, did they score? And most of you answered yes or no correctly. But that wasn't a big deal. I wasn't after if you knew the rules of football and if it had to go over or under to score type thing here. But this was really the question. The question is, what is the height? And so I'm looking for that 1.46. Sounds like most of you know the rules of football. Didn't score. You got to go over the top, not underneath. Okay, so fair enough here. It's not in the goal. Which, so anyways, like I said, I don't think it would be a fair question. Because this was a soccer one that goes over the top, you would said it didn't score. So make sure that, make it clear. And then when I was writing it, I go, well, I said football, but I better make sure it's American football for my international students. I didn't want you to think it was, because if it's, if it's soccer football, goes over the top, it doesn't score. You want to go underneath. Anyway, so I think you get the point. So you didn't have to answer that whether you scored or not. But you did have to answer, what is the height? Okay? That's important. All right, then number 4, and you can kind of see how these are, a lot the same. It's just now that we've gone to 2 dimensions. But you've got to take the motion in 1 dimension, get some information from it, and plug it into the next one. And the same thing happens here for this unfortunate airplane, that the wings fall off in flight. And now it has a horizontal acceleration. And so in this one, we can use, again, the horizontal motion to figure out the time, and then use the time back in the vertical motion. And so that's what I was saying. These first 4 essentially a lot the same. These first 4 chapters were essentially a lot the same. And so I think you guys have caught on, and you're more than ready now to move on to something else, all right? And so let's put this in. The only thing that's really kind of different in this problem is we don't just have a simple projectile motion. Here we continue with a horizontal acceleration. And so once the wings fall off but the prop is still running, we have a horizontal acceleration. It's like the Coyote and Roadrunner one we did in class here. And so, like I said, many of you saw that right away here. You realize that we'll take the place where the wings fall off to be position 0. We're already going 55 meters per second, and what's different now is, compared to the football one, is we do have an acceleration in the x direction. And so with the wings gone, I guess the plane starts to accelerate here. Of course, it starts to fall too at the same time. That's what we got to figure out. But in this case, the question is, how far does it fall when it moves over 200 meters? So this would be the first equation. And if you set this up and solve for time, 3.47 seconds. That number sounds familiar. Did we? Is that close to the first one? Or second one? Oh, yeah. And yeah, that's just coincidental. I don't see any reason why they should be the same. One's a vertical. Wow. Okay. Okay. All right, but so there's the time to go 200 meters here for this airplane. And then once you know that, then you can set up the equation for your vertical motion and plug that in too. And so starting at position 0, and another nice conceptual one that, again, I think everybody saw, so I was happy to see, nobody was confused there, is that your initial vertical speed is 0, not 55, right? And so you saw that, and then the acceleration is the 9.8, or you could call it down as negative if you want to. That's fine. But using that negative 9.8 and the time of 3.47 and square it, you get a negative 59 meters there. And so there's how far down it goes. And that was what the question was after there, is how far down did it go. And then finally, the last one, much different than the other ones, as to be expected. It was different altogether. We just got it here in chapter 4. It was that connection between tangential and radial and total acceleration here. Real quick review, because this is going to take more of a conceptual part first before you can start putting in your numbers and plugging and chugging and getting the right answer here. But as we looked at this and we drew a picture that looked something like this, we said if you had an object and it was headed this way, so if I have an object in a circle and it's heading that way, if you apply a force or an acceleration in the direction it's moving, that would make it go faster. And if you apply it in the direction opposite to its moving, it would make it go slower. All right. And so that's what we said in chapter 2. When we got into chapter 4, we added this piece to the puzzle. What about an acceleration that is perpendicular to it? Makes it turn. And so what happens if you have an acceleration that looks like this, or an acceleration that looks like this? Yeah, you can use our vectors and say this would be made out of a part that is perpendicular and a part that's parallel. So this would be involving a turning because it has that much, but it would also be making it go faster. Whereas this one would have a perpendicular one, which is making it turn, but it also has what we would call a parallel one or a tangential one, which is making it go slow. So in this particular problem, if this is the center of the circle, you are turning in a circle, so it should have a component that way. I'll call it the radial direction. And it should also have a tangential or a parallel one, which is either making it go faster or slower. But this one's very clear that it's making it go slower. So it would look like this. And so this one would be like that. And of course, then when you put those two together, you would have a total. And so the connection here is, of course, Pythagorean's theorem that the radial one and the tangential ones are related to each other to the total one. So the real first step here is to keep track of which one is which and which one is doing which one. So when they say the train is slowing down by 2, which one are they giving me? Yeah, that one there. And if you want to put a -2, that's fine. But remember, negative doesn't mean slowing down always. It means opposite to the positive direction. And that doesn't necessarily mean slowing down. But it could. It doesn't matter. You're going to square it. So put it there or not put it there. It's kind of irrelevant. And the other part is to keep track of what have they given you in terms of the other piece of the puzzle, and they have said the total is 5. So they did not give you the radial one, in other words. So don't use the 2 or the 5 for the radial one, which was, you know, the common mistake to do is you've got to figure out what the radial is. So one of the main first steps here is to find that radial component. And the radial component, when you go through the math here, comes out to be 4.58 meters per second. So there's the radial one. So there's half the problem, if you will. Question?
Yeah. What's the difference between radial acceleration and centripetal acceleration?
Oh, it's the same.
Oh, they're like exactly the same?
Exactly the same. Okay. Yeah, one's just using a math word, radially. The other one is using a physics word, centripetal.
Okay.
Yeah. So maybe I should use centripetal. I don't know. It's meant to be more physicsy than mathy here. Okay. Yeah. It is a word now, right? It's like ginormous, you know. Or gullible, you know. Gullible is not even in the dictionary. That is a real word. That is. But it's not in the dictionary. Go look it up. All right. All right. So there is step 1. What is the radial acceleration? And then once you've got that, then we go back to our little derivation that says that the radial acceleration was related to the velocity and the radius. We went through a little calculus proof for that. Didn't expect you to go through the calculus proof. Nobody did, rightfully so. And then just use that to find the velocity, like you had some homework problems and like we did in class. And so you did. And so putting in our numbers of 4.58 here and putting in a radius of 70 meters leaves us with an unknown speed v. And so 17.9 meters per second is what the speed came out to be there. So there you have it. There's our 5 questions. And like I said, hopefully you did well, and most of you did. And if you did well, great. Keep it up. The good and bad news for all of you is this is only one of 3 tests and a final exam, where the final exam is the equivalent of a test and a half. So putting that in perspective, you've done 1 out of 4.5 tests. So good news is if you keep up the good work, you'll get a good grade. Good news also is if you didn't do so well, you've got plenty of time and plenty of points left over to do very, very well still here. And so if you've looked at the grading curve and the way the formulas are laid out, although I don't drop a test, you can do poorly on one and still pull off the A as long as you get the A's and do all the homework and stuff on the other one. So that's how the math works. So you gotta blow 2 tests though before you drop in below that A. Well, now as I was saying as I got started, oh good, it didn't take too long. I want to jump into chapter 5 and do as much as I can for you. Because again, this will be a step up. I don't know if you bothered to try to work ahead and do some this weekend. If you did, great for you. If not, you're going to have, I think, a little busy week this week as we jump in here to chapter 5. And as you work on these problems, I will put back on the board where we left off. It seems like a while ago since we had a lecture, and I guess it was. It's been, 12 days. Given the fact that we had a holiday and then a test. But here's where we left off. The lecture before the test, we had done some more examples to chapter 4, if you recall. In fact, I myself, was like, wow, what did we do again? I had to go back and look at my notes and think about it for a while, and I even cheated a little bit. I had to go back to YouTube here and go, now where did I stop here? And I did, and when I went back and looked at the old film, I said, oh good, what we did was we were trying to lay out Newton's first, second, and third law to kind of remind you. So that's where I want to pick up here. We were going through this whole idea of saying, what are Newton's 3 laws of motion? And you've seen these 3 laws before, you just haven't seen them with your vectors before. And you certainly haven't seen them with as many forces or with calculus. And so that's what will make this chapter different than your Physics 102. You might remember we left with this hockey puck. So I thought I'd throw the hockey puck back up there. And I don't even see the hockey puck now. Huh. This is chapter 5. Anybody see the hockey puck? Up at the top? No, I don't think it was one of these. Well, that's weird. Ah. Guess I didn't go far enough down. I figured it was at the beginning. But this is, yeah, this little hockey puck here where we have left off here. And like I said, I don't think the general rules, if you will. The three laws are going to be hard for you. It is, could you apply them to problems that have lots of forces and using our vectors? And I'm thinking so. It's not like it's a major step, but it is saying, let's put our math together with our physics. And so the math that we've learned here in this class, plus the calculus you learned in the Math 150, plus the physics you learned in 102, and when you put all those two together, you're going to see this chapter. And so that's the idea here. So I will put number 1 up here and say, okay, what was the law of inertia? Well, anybody got it memorized? Repeat it. Okay, it's resistance to change its state of motion. That is what inertia means. But it says if you have an object at rest, it remains at rest. An object in motion will remain in motion. What kind of motion?
Constant.
Constant what? Velocity. Velocity means constant what? No. So constant direction and constant speed, right? All right, so an object at rest will remain at rest. An object in motion will remain in motion with a constant speed and constant direction, or a straight line, unless acted upon by a net force. And so there's our new word, that net force. And as I was saying then, is anytime you see something that goes faster, slower, turns, what you know is there must be a net force on it. If it is not going faster and not turning, then there is no net force on it. And the second law then picks up where the first one stopped. The first one said there will be an acceleration. The second one says what is the value of that acceleration. And so there's our equation. And as you will see again and again, and I might as well joke with you again, I know I said it before and it probably wasn't funny then, but do you want the answers to all the homework problems for this chapter? And for that matter, it's the answer to half of the test that comes up in what, 4 weeks, 5 weeks, 4 weeks. There it is. I mean, this is all we're going to do for the next 2 chapters, is Newton's 3 laws of motion. And only one of them, right here, has a formula in it. And it says, look, just take all the forces, add them together. That is your net force. You divide it by its mass. That is its acceleration. Okay? Notice they've got vectors on them. So when we left off, we actually tried that. We said, look, here is an object, and they've gotten 2 forces. This happens to be a hockey puck, and you know they dropped it for a little face-off, and the 2 kids hit it, and one hits it with a certain force, looks like 5, down at some angle at 20 degrees. The second one hits it with a force of 8 at 60 degrees, and we had to calculate then what was the total force. And I believe it came out to be just a hair over 10, and so we had a 5 and an 8, and came out with a 10, and the angle was something, you know, off to the side, something like this, okay? And let me not go through it again because I'll have, I think, deeper examples that we need to see now here. But hopefully that jogs your memory, since this was, you know, a test ago and 12 days ago here. But that's what we're going to do. We are going to draw the little picture. We are going to draw the little forces that are on them, and from them add them together, divide by the mass, and we will get the acceleration. This little diagram, by the way, has a name. Maybe you remember it from 102. It's going to be very important. You're going to hear me say it all the time. What is it? Free body diagram. What do we mean by a free body diagram? Yeah, disregard all the other objects around it. Just draw the one object you're interested and the forces on that object. So in this case, do you see any kids? Nah. You see any hockey sticks? No. You barely even see the ice. I think that blue and white there is supposed to kind of indicate the ice. But probably better not to draw the ice either. All we want is the object, the hockey puck and the forces on it. And that will help condense our thought process to what happens to that object. Because what happens to that object is a consequence of the forces on that object. It doesn't matter where they came from. Of course, to draw the free body diagram, we have to understand the bigger picture of where they are coming from. Don't get me wrong, because, you know, we have to know how many hockey sticks are hitting the puck. If there are 2, then we draw 2 forces. If there are 3, then we draw 3 forces, and so forth and so on. So we do have to understand the bigger picture. But you're going to hear me say that. And I'm going to give you a little recipe here for solving these problems that I think will be very useful if you kind of commit it to memory. The truth is you can't help but to commit it to memory. You're going to do so many. But that first 2 steps are what I want to focus on in these next half hour here. Is like, number 1, got a good physical picture of what's going on. Number 2, draw the free body diagram. Okay? And so that's what we were beginning to see. I didn't use the fancy word free body diagram last time, but that's what this is. This is the free body diagram. This is the force on that object. So when I go to figure out what the acceleration is, I can then just write it out. Now, where I wish I would have gotten is to the third law so that I could really jump into examples here. But I didn't, so let me make sure I cover that now. But I think you know it. This is often referred to as the action-reaction law. Maybe you recall it. What does Newton's third law say? All right. This is the one involving 2 different objects. Your author does a good job in here with 2 planets and a hammer and a nail. He gives this one here, and he says, let's do this. Here is 2 objects. He's got a brown one and a green one. And the 2 objects are interacting with each other. Of course, then the brown one is being pulled by the green one. So the green one, in return, is pulled by the brown one. Make sense? And so, to save some time, I won't write it out. You can read it. But if object 1 puts a force on object 2, then object 2 puts a force on object 1. And how do those forces compare? Equal in magnitude, but opposite in direction. And do you see that in the picture? Look at the notation he uses here. He's saying this is the free body diagram for the brown one. This is the free body diagram for the green one. Okay? What forces are on the brown one? Well, in this case, there's nothing else around, so he's saying there's just one force. It's coming from the green one. So look how he labels it. He labels it from number 1 on number 2. So how would you label the force on the green one? From number 2 on number 1. How do these 2 forces compare? Equal in magnitude, opposite in direction. So that's going to be our notation. And I suppose you might call this some math too. But the real math is going to be right here in number 2. This will just tell us, hey, we've got 2 forces, they're equal, they're opposite. Yeah?
What if like one object was going toward the other object and it was making the brown object go away? Would that still be action reaction? Like magnets with the thing where you push them and they go away.
Okay, oh yeah, now this is showing 2 objects being pulled together. If they were being pushed apart, like by a spring or by a magnet, same thing. I would just probably draw them like this. Let me draw them for you, but I would still have them equal and opposite. And that's the key. It's many of you might remember for 102, I often do a joke and try different things. And I'd say, well, what if this is a big object and a small object? Does it matter? What if one's pushing and one's pulling? It doesn't matter. So if you have what you said, something like this, then I would have to label it something like that. But I would still say, this is the force, and I'll use the same numbering. He's calling this object number 2 and this number 1. So this is the force on number 1 from number 2. And so this over here would be the force from number 2 on number 1. And so again, they're equal but opposite. So again, doesn't matter pushing, pulling. Doesn't matter if they're big or small, square or round, blue or brown or green. It doesn't matter if it's Tuesday. Even the second Tuesday of next week might work. I don't know about that one. But don't make it too hard, is that's what I'm really getting at. Because it's going to get hard enough on its own. But these 3 laws, one separate by itself, are really supposed to be that easy. But because so many forces can be involved, these problems can get pretty complicated. So you'll have your chance to do the homework this weekend and see, does it seem hard to you or not, when you start putting all the forces in.
So what is it? Just to clarify a little bit, what's the same magnitude? Why do they have the same magnitude?
Why do they have the same magnitude?
How do they have that same magnitude? I don't understand how they're equal.
I'm not trying to explain how they're equal. I don't know how they're equal. That's nature made that.
Oh.
We discover it. So it's Newton's laws of motion. Why does every time when I push on something, I push on it, push it on me? Does it push back harder? No. Less? No. Same? Yes. Every time. Okay? So, and that's,
So it can
discovered.
the larger,
Not proven, discovered.
the larger object cannot pull or push as much as the smaller object because that's
Sure.
mass.
Right. Right.
Okay.
You're playing a game of baseball and in comes the pitch and somebody hits it with the bat. Did the bat put a larger force on the ball or the ball put a larger force on the bat? Equal, right? As sick as it may sound, somebody gets hit in the head with a baseball bat. Bat hit the person in the head pretty hard, right? But the person who got hit in the head did what to the bat? Yeah, hit it back just as hard, So, remember that. Especially if you're on the losing end of a fist fight, right? It's like, I hit his fist so just as hard as he hit it. Exactly the same amount of force. All right. So, again, conceptual ones, but real important. You got to see those because we got to see what the forces are before we can add them together. Watch. What's the net force here? It's not 0. It's not even twice. I guess the best answer is, what object do you want the net force? For those of you who are saying it's 0, you're adding the two together. But now wait a minute, that's not what I said here in the second law. The second law says, what do? You get the net force on an object by adding all the forces on that object. So why are you adding the force that's on the brown together with the force on the green? That's the mistake. Don't do that, right? Somebody asks how much money you have, you wouldn't get into your friend's wallet and say, well, I got this much. That's just inappropriate. The same thing here. You add the forces on the brown object to get the net force on the brown object. Period. End of story. So the net force on the brown object is just F12. It is not 0, and it is not twice. What is the net force on the green object? F21, which you could say is the same magnitude as that one. All right, so when I ask what's the net force, you could say, well, the net force is the same on each of those objects. Sure, and it's the same magnitude as F12 or F21, however you want to look at it. They are obviously clearly in opposite directions. So when you have an acceleration, they are clearly in opposite directions. And sure, this one is going to accelerate that one, and this one is going to accelerate this way. They're attracting. If you had things repelling, the same thing would happen. You would have this one accelerating that way, and this one accelerating that way. Am I at all saying they're going to have the same acceleration? No. Why would they be different? Yeah, I would come over here and say, look, this is going to be the acceleration of number 2, and it will be the net force divided by mass number 2. Whereas this one over here, I will have acceleration of number 1. And acceleration of number 1 would be the force from number 2 on number 1 divided by number 1. And since these two guys have a good chance of having different masses, they end up having different accelerations, even though they have the same force. And I think that's why it gets hard for sometimes students to believe that the forces are the same, because you don't end up with the same acceleration and you don't end up with the same speed. And if these are different objects, like a rig truck running into a bumblebee, you don't have the same structural integrity. But when those two collide, how much force does the truck put on the bee compared to the bee on the truck? The answer is the same. Right? It's exactly the same amount here, even though you have other things that are different. So there's the third law. And like I said, I was hoping that this is where we would leave off. So this is our first 3 laws of motion, right? Our only 3 laws of motion. Do they work all the time?
There's some mechanics.
In other words, are there any limitations here? Do we have anything that we have to watch out for? And there really is 2. Your author talks about one right away, and another one just kind of throws it out there and says, we'll worry about that when we get all the way into chapter 39, so we won't have to worry about it for a while. The first one was known by Newton. And Newton said, look, be careful here. If you don't use these 3 laws correctly, you are going to get into trouble. And so Newton called these inertial reference frames. So let's make sure we apply them correctly. What did he mean by this? Well, let me give you a silly example here. Let's say this goes on. There is a car at a red light. You're the driver of the car. And the light turns green. You step on the accelerator, or maybe I should say the gas pedal, since they're all accelerators. But you step on the gas pedal and you start heading forward. Okay? Now, if you were to watch that motion from 2 different perspectives, let's think about what you would get. Let's say you are outside of the car. So you are standing on the sidewalk. Light turns green here on Cliff Drive. You're leaving school. You stop. Light turns green. You watch that car pull on out. What you would do is you would say, well, that car is accelerating. And because it is accelerating, you would say there is a force on it. Fair enough? And you would be right. And you could trace this all down to the traction between the tires and the road, and the pushing of the tires, which come from the transmission, which comes from the engine, and so you could break that down and break it down correctly, and everything would look just fine. But if you're in the car, you could easily make this mistake. You're in the car, light turns green, you step on the gas pedal, and you look at the buildings around you, and you see them all accelerating towards you. Now, are they accelerating or are you accelerating? See, from your perspective, you may say, hey, those buildings are accelerating. And if you do that, then you will say, well, let's apply Newton's laws to those buildings. And if you apply Newton's laws to those buildings, you would say, well, there must be a huge force on those buildings. And you start looking for this force and this engine and this burning of fuel somewhere, and you won't find it. Things won't add up. It just won't work. And you'll go, something is really wrong with Newton's laws of motion. And I would say, yes, you use them wrong. Because you can't use them in accelerating reference frames. Inertial reference frames mean no acceleration. So you have to be looking at the world in a frame that is non-accelerating. If you are in an accelerating reference frame, you are in a non-inertial reference frame. And things will not behave right. They will not follow Newton's laws of motion. And Newton knew that and made it very clear. And so your author takes some time talking about inertial reference frame. Revisit it in chapter 6. You might be happy to hear that actually doing these 3 laws of motion are quite hard. So we will have 2 chapters and 2 weeks to do them. We will do all this fun stuff in chapter 5, only to continue it in chapter 6. So we won't learn any new physics into chapter 6. We will just extend it to different accelerations. You'll see in this chapter, all of our accelerations will be faster, slower, and straight lines. God, how easy can this chapter be? Faster, slower, straight lines. God, looking forward to it. It's going to be an easy week. Because then next week we'll do the same thing, except now we'll turn. And we'll have air resistance. Okay? And all of those will just be a little harder mathematically. But nonetheless, still the same physics. Okay? And also in that chapter 6, we will say, well, what happens if you're in an accelerating reference frame? How are you going to handle it then? Because that does happen a lot. And what are you going to do? So, I'm not going to worry about it this chapter, other than to tell you that as we go to apply Newton's second law, or for that matter, first or third law, just make sure you are in a non-accelerating reference frame. If you got yourself pictured in the car accelerating, step out of it and analyze the problem from outside, standing on the sidewalk, okay? And say, okay, look, I've got to be in a non-accelerating reference frame. So like I said, that's one that if you it's easy to get out of, but you got to make sure you recognize it. And Newton himself knew that and made it very clear. These are the 3 laws of motion, but they can only be applied in inertial reference frames. The second one, Newton knew nothing about, and it wasn't until Einstein that began to realize that, wait a minute, these laws don't seem to hold out when we're getting close to the speed of light. And so as you get close to the speed of light, you can't use F equals ma anymore. Darn. Okay, now we don't like to say Newton's wrong, but we at least like to say Newton was incomplete. So we'll have to learn more in terms of our science and our engineering. Fortunately, our cars and our planes and our boats and even our satellites and our rocket ships don't even go close to the speed of light. And so for the most part, F equals ma works fine. And other than a few cases, like these big atom smashers where the scientists get their atoms going close to the speed of light, everybody just uses F equals ma. So, if you find yourself someday, launching a satellite or building a new engine and electric motors or, whatever engineering you find yourself in, F equals ma is fine. You can come think about your days back in college. I remember when Dr. Young said there was something different, but we never use it. Probably true. Okay. There was a time, and we've kind of got away from it, but these old monitors, we don't even have any anymore, but the old CRT, the big monitors, not the flat screens with the LCDs, but the CRT tubes, those were illuminated. And the reason they had depth to them, if you remember them, is they had electrons in the back that would race the 18 inches of there and hit the screen. And they would get going close to the speed of light. And so the electrical engineers found out that they could not use F equals ma. And so as the resolution got better and better and these electrons went faster and faster, they found themselves in an interesting predicament. And they go, oh, I remember my physics teacher back in college saying, maybe you can't use F equals ma, but I've been using it for 35 years and now I can't get the screen resolution to come out right. And it's true, you can't. The GPS satellites are the same way. That it's not that they're going all that fast, but there's some other issues that come into play. And so unless you're designing the GPS system, F equals ma is just fine. So what I'm trying to say here is let's learn these. Let's know that there's some limitations. We'll revisit this in chapter 39. We'll discuss this more in chapter 6, but this is where we get started. Newton's 3 laws of motion. So let's look at some forces here. Obviously, the game plan here was to say, okay, when you have a couple of objects and they push and they pull, the idea here is to draw a free body diagram and look to see what its acceleration is. A good one that your author sets up here is he's got, speaking of old monitors, he's got an old monitor sitting on a table. I'm just having a hard time finding anything here. Oh, there it is. And so here is this monitor. I told you it looked pretty old school here. And it's sitting here on the table. Let's look at some of those forces. Because what I want to get across in the hour that we have left here is the strategy to solve this. Number 1, good physical picture of what's going on. Number 2, draw that free body diagram. Okay? Label those forces. Then write out the equation, solve the equation. Okay? And I think this part, writing out the equation and solving it, is probably some of the easier stuff. It is, do you see all the forces? Did you set it up right? Because once you set it up right, then we can do the math. And so this chapter, more than any of the other chapters we've had so far, is definitely physics. It is half physics, just setting it up right. Then once you set it up right, you have math, and you got to solve the math. But if you don't set it up right at the beginning, you can solve those wrong equations correctly and still end up with a wrong answer. Okay, you got to have those first equations correctly. And so let's see this in action in probably the simplest case we can get started. I'll start with, got a good physical picture of what's going on? Got a free body diagram. I'll start with here with the good physical picture. Here's all they're trying to do. They're trying to say, look, let's take a room. Looks like it might be a kitchen since it has tile. So we've got some tile. We've got a tiled room. We got a table. And on top of that table is a monitor. Fair enough? Thinking about that monitor for itself, what is the net force on that monitor?
0.
It's 0. Why? Why do I know that? Just right away, without really much thought. Because it's not accelerating. I don't say not moving, because could you be moving and have no acceleration? Yeah, right. You could be moving at a constant speed in a constant direction here. Okay, but that's not what's going on here. This is true. It's not moving. But more importantly than not moving is it's not accelerating. And if it's not accelerating, what does Newton's second law tell us? Yeah, no acceleration means the net force is 0. Okay? All right, so fair enough. Good physical picture, because look at this jump over to here. The jump over to here is what I would call, now draw the free body diagram. What forces are on this monitor?
What is EM standing for?
Well, and then that's kind of,
E is something else.
and oh, that's, okay, and that's what I'm going to get here. I want you to see some forces. For us to be able to solve this, we need to give you some basic forces. One of them is the force of gravity. Another one is what we will call a normal force. Another one is what we will call a friction or a frictional force. And then we can have other forces, something like a rope could tie to it or kick to it. So anything that makes a contact would be a force here. But let's look at some real basic ones to get us started here. And that's what the monitor, is the monitor being pulled down by anything? Yeah, what is weight then? Okay, weight is a force. Now, as we're going to soon learn, we can calculate it by mg, if you remember that from 102. So let's go through that same idea here, but this is a force. This is a force. It is from where? It is from the Earth. Now, without getting into how gravity works, although we did that in 102, and we will again when we get to chapter 13 in this book here, and we get to Newton's law of gravitational forces, not worrying too much about that yet, but I think you are well aware of the fact that the Earth pulls things to it, right? It's called gravity, okay? Again, not so much why, but discovered. Hey, we know that all objects attract every other object in proportional to a product of the masses and inversely proportional to the square of the distance between them. So there's Newton's universal law of gravity. But like I said, without reviewing that or going into Newton's universal law of gravity, you need to realize then when you have an object, there's going to be multiple forces on it, and one of those will be the force of gravity. And so gravity is a force, and it comes from where? The Earth. So as I look at this monitor, is this monitor being pulled down by gravity? Yes. And that's what is trying to get labeled here, which your author puts, and he labels it either F sub g for force due to gravity, or he labels it as force from Earth on monitor. And so there's our symbols again. So the big E is for Earth, the little m is for the monitor. So whoever was asking about what that notation was for, that's what it is. So saying, look, there is a force pulling it down. That is the force of gravity. That's one of many forces we're going to have to think about when we solve all these problems. Yes?
Then the other one with the arrow going up.
So what else is going on here? Yeah, is there anything pushing up? I mean, what if that table wasn't there? Okay, go ahead.
Does the gravity depend on where you are in the universe? Would the gravity be different if you were centered at the sun from Earth?
Yeah, let me go back to Physics 102. Force from gravity depends on the mass of the two objects and the distance between them. So as we get further and further from the Earth, our force of gravity gets less and less and
Well, I
less.
mean, if you have your origin at the sun, or an object on the Earth, the gravity would be...
Oh, well, okay, so if you're talking about an object that is on the surface of the Earth, and you're talking about the force of gravity from the Earth, it doesn't matter where you put your origin.
No, it's like if you started at the sun and wanted to calculate the gravity of
So here's the Earth, here's the sun, here's the object. Okay? If you want to know the force on this guy from the Earth, then you need to know the distance between them. It doesn't matter where your origin is. If you wanted to know, in addition to that, the gravitational force to the sun, then you need to know that distance. The total force, then, is the total gravitational force of those two vectors. The force on the object from the Earth plus the force on the object from the sun plus the force on the object from the moon. See where I'm going? Does that answer? So it doesn't matter where I put the origin, although putting the origin here might help me with distances better, you know, versus putting my origin here. It's my choice, but the calculation of the force of gravity is not just one calculation. The force of gravity comes from every object. But we'll ignore the sun, we'll ignore the moon, we'll ignore the gravitational forces of the buildings, okay? We're going to ignore all those and just say we get most of our gravitational force from the Earth. And so we'll only deal with one right now. Okay, but more on that when we get to chapter 13, okay? Okay, so back to this, one of the forces is the force of gravity. And as somebody pointed out, aren't there other forces here? And there are. But let's just say we had only the force of gravity. In other words, what if that table wasn't there? What would happen to this monitor? Yeah, I would say there is this force of gravity. And what would its net force be? Well, it would be the force of gravity if there was no table there, right? Net force says add up all the forces, and if all you had was just the object with the Earth, no table, table's not touching it, right? Table can't put a force on it, so the only force I have is the force of gravity. That must equal to ma. And then what did we say the acceleration was? That's our g, or 9.8, right? And so, what I'm trying to say here, as some of you already pointed out, is one of the forces is the force of gravity. How do we calculate it? mg. So we see that by applying Newton's second law to the case where it is all by itself, no table, and so there's our force of gravity. And your author does not list it in here, but if he was, this would be a good place to put it. The force of gravity does equal mg. Yeah.
Does the force of gravity get less and less the deeper you go?
It does get less and less the deeper you go.
You get to the center and you just kind of float.
Yeah. And I'm not sure saying less and less is a good way of putting it, as much as if you can imagine yourself in the middle of the Earth, you would have half the Earth below you pulling you down and half the Earth above you pulling you up. The net force of those two is 0. Yeah. And so you would, you know, as you said, just kind of float there, if you will, because you would be pulled equally, kind of like we're going to do with this monitor. This monitor is going to be pulled equally. It's getting pulled down by gravity, but in a second we'll see it's getting pulled up by the table.
Is there a point where you discount, like, if it's on a slab of tile?
Yeah.
I mean, you sort of negate those forces?
What forces?
Or Or, I mean, when does gravity, you know, is it on bare earth or is it on, you know, that spacing of whatever it's on?
No. Gravity is, now maybe I'll go a picture. Gravity's a field force. Gravity you're always going to get. If you don't have a table there.
Well, I mean, like, when do you negate the fact of, like, say, the table? Say if instead of a table, it's just a piece of tile.
Well, then the tile will be pushing on it.
I think he's saying, like, what if you're in a building on the 50th floor and then on a table and then you have the computer, like, when you
What
disregard
I'm saying is like, you got your ground, your earth,
Yeah.
and then you put, say, like a quarter-inch tile. I mean,
Yeah.
so you add that quarter-inch tile into the effects of, when you sort of, at what, say, point do you negate whatever surface it's sitting on?
Oh, I guess I'd say I'm already doing that. For example, if I'm on the first floor and I drop, what's the acceleration? 9.8. I go to the 50th floor and I drop it. What's the acceleration? 9.8. So I'm already saying that the height of the building is irrelevant. You'll see that in the math. Again, good questions. You're all jumping way ahead, really, though, to chapter 13. But the radius of the Earth is over 6 million meters. So when you say take 6 million meters and add another 50, big deal. So I'm already ignoring another slab of cement and another height of the building and another mile up. Yeah, it's just not that much of a difference. I would have to get all the way into outer space before it really changed anything. And so what you'll see is we will say that the acceleration is 9.8 anywhere humans are going to be without a rocket ship. So that will change when we get into chapter 13. Then we will say, hey, remember the radius of the Earth was 6 million meters, and that seemed like a lot. But now we got to think about it now that we've gone up 1 million meters. So then it'll start to matter. So I guess the short answer is, unless you get out of the atmosphere, don't worry about where you are in the atmosphere. It's still going to be the same number. And this is how you calculate it. That's what I was trying to point out. So anywhere in the atmosphere, one of the forces you will need is the force of gravity. So there's one of 3 important ones I want to get started with. Back to this monitor again. Okay. There we go. All right, so back to this monitor. There is one of the forces. And again, wanted to make sure I pointed out the notation as well as had calculated. But as you guys pointed out a few moments ago, that's not the only force on the monitor. What else is happening to this monitor? Yeah, the whole reason it's not falling is the table. Is the table doing anything? Yeah, and it's a little difficult to start explaining on the molecular level, but if you have had any chemistry, and I would assume at this point you've done a little bit, I mean, these atoms push through an electrical force. And so anytime something touches, like why does my hand stop when it hits this table? What? Yeah, it's these electrons here that are repelling these electrons, and there's an electrical interaction that's going on here. So anytime we have contact with something, whether it's my hands pushing on a table, or whether it's my foot pushing on a table, but anytime there's actually a physical contact, the molecules are pushing on each other. Not through gravity, but some other force called an electrical force. So it's probably easy for us just to say, look for things that are in contact. If they're touching, they are putting a force on each other. So, is that monitor touching the table? Yes. And so it's those molecules that this table is made out of that is pushing on the molecules that the monitor is made out of and is putting a force on it. And so that force happens to be in an upward way. That's why it doesn't fall down. Without the table, it would have fell. Without the table, it would have had the force of gravity. And notice, I'm not saying that all of a sudden you put a table there and gravity is shut off. That's not what I'm saying. What I'm saying is gravity is still there, except it doesn't fall because you now push up. And so there is an additional upward force. And this force that is perpendicular to the surface is called a normal force. Maybe you're familiar with that word for math. What do you call a line that is perpendicular to a plane? A normal, right? And so it is perpendicular. So we're going to use that wording from our math class. That anytime we have a surface and it's pushing perpendicular, okay, not sideways, that's coming up. That's the next one, friction. So friction will be tangential along the surface, okay? But the stuff that is pushing upward, okay, that is called the normal force. So this is coming from the surface. It is from those molecules. And your author then labels it as a little n. And so if you look in this little diagram here, he says n is pushing up. And he calls it FTM. Why do you think he calls it FTM? From the table on the monitor. Okay, so once you start seeing the notation, you begin to see that hopefully these things make more sense. Who was raising their hand? Question.
I think I got it.
I was wondering, how much is the greatest amount of force that any object can have? Like, can you find that? Because if the table wasn't strong enough and couldn't support that kind of force, it would break. So how do you know what the most force it can exert?
Well, okay, great question, and certainly well beyond where we are right now in our science. But yes, this force is coming from the molecules. So the molecules got to be strong enough to push up. We know molecules are only so strong. You know they can break apart. And so if you have enough weight on this table, those molecules cannot supply enough upward force, and they will separate.
Can you measure how much it could support?
Could I measure it? Yes. Sure. I mean, which is very common, right? You take materials, you take them into the lab, you pull on them until they break.
Right.
And you go, what is the strength of that material? Okay. And many of you will probably be taking the next semester the strength of materials, and so you'll realize how strong steel is, how strong concrete is, how strong nylon is, and silk, and you'll go through all your materials and you'll say, okay, now I got to build a bridge, and this bridge has to hold this many cars. How much steel do I have to make this? How big do the I-beams have to be before this thing will break? Okay, so great questions, but again, much further along than this introductory course of or maybe I shouldn't call it introductory course. That was a Physics 102. This is more of the Physics 1, but much more than a Physics 1 course here. But yes, there's obviously a limit here, right? But notice again, it's from that surface. So in the diagram here, we should have a force N pushing up. And so sure enough, you have that in your free body diagram. So this is the forces on our free body diagram. These are the two forces on the monitor. Yeah.
So if you took away the table, you'd still want to write the force of the monitor on the Earth?
Well, okay, so now this is where you got to be real careful. Here's where you can get yourself confused. Very simply here is if you want to study the monitor, then write all the forces on the monitor. If you want to study the table, then write all the forces on the table. And that's what I'm trying to get here in this half hour is, do you have a good physical picture of what's going on? Step one. Step two, then draw the free body diagram, which includes the forces on just the object you are interested in. If you'll notice, there's no table here. And there's no forces on the table here. Are there forces on the table, though, in reality? Sure. There's a lot of forces on the table. And that's what I think this one is supposed to represent. What's this one saying? Force from the monitor on the table. It is equal and opposite to that one up there, which is the force from the table on the monitor. So that's where those came from. We know they're equal and opposite. Why? Newton's third law, right? So Newton's third law is saying, look, the table right here is putting a force on the monitor. So the monitor is putting a force on the table. Fair enough? Those are your two objects. They are equal in magnitude, opposite in direction. But when you go to do the free body diagram for just the object, do you put this force over here? No, why not? Because it's not on the table. It's on the monitor, right? And so that force does exist, I just haven't drawn it over here. Are there any other forces that exist that I don't draw over here? Sure, what's this one right here? Yeah, it is the equal and opposite to that one. Didn't we say that the Earth was pulling on the monitor right there? From the Earth on the monitor? So if the Earth is pulling on the monitor, then the monitor is pulling on the Earth. And so there is a force right here on the Earth. And that's what this picture is supposed to be. It's supposed to be on the tile. The Earth is being pulled up. If there was no table here, if this was the monitor by itself, and this was the Earth down here, there would, of course, be the force of gravity on the monitor, and then there would be the force on the Earth, or from the monitor on the Earth, pulling the Earth up.
Isn't that so small?
Well, is it small? How does this force compare to that force? They're equal, aren't they? Now, would you get the same acceleration of this monitor, 9.8, as the Earth coming up? No, why not? Different masses, exactly. So I wouldn't say that the force is small, but I would say it results in a small acceleration. So we never think about the Earth coming up. You know, I don't stand up here and say, I'm going to drop the book. Hang on, guys. I mean, did you feel the Earth come up? No, absolutely not. But isn't the force on the book from the Earth the same as the force on the Earth from the book? Aren't they equal and opposite? All right, so I'll say it again. It's Newton's three laws, and they really are supposed to be this simple. They're not really hard until you start sitting down and looking at all the forces on all the objects. And that's why we often don't. We often then separate into a free body diagram just the object we want to study. Okay? So this free body technique is very important. That's why I said there's 4 steps here. And I don't even want to do all 4 quite yet. I just want to say, do you got a good physical picture of what's going on? Did you draw the free body diagram? Start there. Because once you do that, then we can write out the equations and then we can solve it. Okay? But the first step is what I'm trying to, or first 2 steps is what I'm trying to point out in here. So I have not drawn a lot of the forces. In fact, I would say the author hasn't even bothered to draw all the forces on here. Can you think any that might be missing here?
The table.
The legs of the table.
Right. I mean, he has not included, for good reason, that there's a contact between the table and the Earth. So wouldn't the Earth be putting a force on the table and the table putting a force? So shouldn't there be 2 more right here? Now, not drawn because there's no way would we need those over here. They have nothing to do with the monitor. But the way it stands right now, with the forces he's drawn, he has a net force on the monitor of up and down of equal. That makes sense. That's what he's trying to study. But if you look at the table, he's got a force on the table pushing down, and that's it. And that would tell me the table goes down. But the table doesn't go down. Why not? Because he hasn't drawn the normal force between the table and the ground. He also hasn't drawn the force of gravity from the table. So I would say there are 2 other forces on that table that aren't even included in this picture. And if they were asking me something about the table, I better include that. And for that matter, we don't have the other forces on the Earth, those same equal and opposite ones. If the Earth is pulling on the table because of gravity, then there should be then an upward force due to gravity from that table. As well as there should be another force on the Earth from the contact that is between this table. So we're missing 2 forces on the table, we're missing 2 forces on the Earth. We don't have everything up here. But I think if you see everything, you'll be enlightened to be able to solve these problems. You have to see all these forces and then make sure you write them out correctly. If you miss something, well, that's when you run into troubles here. Watch, he throws some other ones out here in the reading here to kind of get you to start it. Besides doing the monitor, he kind of does the chandelier here. Okay? And again, he's just trying to get these first 2 steps. Do you got a good physical picture of what's going on? Well, we got a chandelier. It's hanging by a chain. Okay? and it's not accelerating. So now, the next step is free body diagram for just the chandelier. There could be many other forces involved. Don't want to miss any, but I only really care about the ones on the chandelier. So, what are the forces on the chandelier? Obviously, the force of gravity. And so he labels it F sub G. What else? Yeah, the force from the chain. That would be the molecules in the chain. Now, he calls this a tension. And so he puts there tension. So I should put that one. But again, it's, you know, from the, in this case, the chain. It could have been a rope. Either way, it's from the molecules here. But that is one other force that we got to make sure we pay attention to. So I'll say it again. Look for anything that is touching the object. You will get forces from it. Plus gravity. Gravity doesn't have to actually touch it. It's what your author calls a field force there. And so gravity does not need to touch. You can hold the pen way up here above the surface of the earth and it will still get pulled down. Your hand, on the other hand, has to actually come over and touch it. The molecules have to get close. The rope has to get close. Your foot has to get close. You know, whatever it is, it's got to actually make contact here. So in this case, there's only two. And in this case, how do these two forces compare? Are they equal? I would say they are. Why? No acceleration. Right? You would come over here and go, Newton's second law says the acceleration is zero, so the forces must be equal and opposite. Whereas, he's also drawn the free body diagram for the chain. And notice he says the chain is being pulled down. And he asks, how do these two compare? And I'd say those two are equal. They're on different objects. How do I know they're equal? And it's not because of no acceleration. Third law, action and reaction. Did you catch that subtlety? Okay. That the chain is pulling on the chandelier, so the chandelier is pulling on the chain. Equal and opposite.
That's the same thing with the chains in the ceiling.
Right, and then we can extend this up to the ceiling and say, well, the chain is pulling on the ceiling, so the ceiling is pulling on the chain. And they don't show the force on the ceiling. He just shows the force on the chain right here. But there should be another force there on the ceiling. And those two would be equal and opposite because of Newton's third law. But as we look at the chain, how would these two forces compare? That one and that one. They would be equal and opposite. Why? Third law or second law? Second law, right? They are on the same object. They have an acceleration of 0. So we are adding forces on the same object. So remember that when they're on the same object, they can't be Newton's third law. Third law is different objects. Object 1 puts a force on object 2, so object 2 puts a force of equal and opposite back on number 1. Okay? And so there's just, again, some subtleties in here, some logic that we got to go through. Yeah?
Is that T prime?
Well, he calls it T prime, but don't think of that as T like a derivative. He probably should call it T1 and T2. He's just trying to give it a different notation to make you think about, is T the same as T prime? Yeah. He doesn't want you to think it's a derivative. That's for sure. Just a different notation. So, yeah. Fair enough? Well, let's try a couple of others here before we even, start to do any type of calculation or anything in here. How about this person here? You got a person, they got this big old...
You put freeze. Unfreeze. It's frozen. The bottom.
Oh! I must have done it with this one. What did I push? Freeze on here. What did pause? Play, see, sound. Oh, wait. Yeah. Okay. Okay. All right. All right, so on this one, let's look at that big box. So this person, ties a rope on it, starts pulling this box, drags it across the floor. So we got a box, we got a floor, we got a person. Got a good physical picture of what's going on? See, that's step one. What is going on? What's the physical picture? Okay. Step two, do you see the forces? Of course, now this is the part you got to stop and say, well, what are we interested in? Are we interested in the person? The box? The floor? And I think in this problem, they're interested in the box. Okay, so let's focus on the box. What forces are on this box? Yeah, you're beginning to see it. It says, okay, so here's the box. And they list 3 forces. The T is from the tension. Okay, the rope is obviously tied to it and it's pulling along the rope. But anything else? Yeah, there's still the force of gravity pushing down on, pulling down on the box. Anything else? Yeah, then there's the normal force. And so here we have those. Now in this case, I would say there's probably some friction also, but we haven't talked about friction yet. So the author hasn't included. So I guess in this case, we're dragging it across a floor made out of ice or something here. And, it's probably not realistic. But he's saying no friction there. But you're right. There would be another force here. There would be a force of friction. And so maybe now would be a good time to throw that one in there. And so that's my whole point. Once we talk about these 4, I think you're ready to do any and every problem in this chapter. Just look at the forces, see which ones they are, label them out in a free body diagram, and write out the equation and solve it. Oh, friction. Friction. All right. So let me jump to a picture where your author had some friction. So if you've got a chance to read it, which I hope you did before you came here, that you will see that he starts with some simple ones without friction, and then eventually leads up to ones with friction. In fact, to work in friction, he does a good one with a trash can here. And he says, let's go ahead and look at a trash can that's sitting on some floor. So it looks like it's a concrete floor. Maybe this is a trash can in the center of your garage here. And he says, let's grab the trash can and begin to pull on it. Because of all of these, I think the hardest one right here is the friction. And he says, well, let's just start dragging it across. But he says there's something interesting that happens here. First of all, how many forces are there? Well, okay, if this is it, that would be my hand to me. So there's what he labels capital F. Okay? Then, of course, isn't there gravity pushing it down? Okay, so there's the mg right here. And then, of course, there's the ground pushing up. But then the new one is right here, which he calls friction. But he breaks it into 2 categories here. Okay? The first part is when the object doesn't slide. He says, look, if it doesn't slide, there is what we'll call a static friction. But once it does begin to slide, then something else happens. And so it's friction, but it's really 2 categories here. Let's start with the first category. This S, this static friction. So he calls this F sub S as opposed to F sub K here.
So when you said static
in the
friction, when it's sliding or
static means no sliding. Okay? So let's see, this one can't actually move, but this one could. So here's this trash can. Okay? So what I could do, I could push on this. And if I push just a little bit, it won't move. Think about the forces then. If I push just a little bit and it doesn't move, why not? What else is going on? Something else is pushing back. Right, and your author shows, I think, a good picture. Right here, he tries to take a magnifying glass and blow it up. He says, look, let's look down between the trash can and the floor right here. You'll see that on a microscopic level, there's some rough edges. And so as you try to push, those molecules tend to lock into place, maybe something like this, and as you try to push sideways, they push back sideways. They're already pushing up, right? That's where the normal force comes from. But in addition to that, they can push sideways. So really, both of these forces are coming from the same place. They're coming from the molecules of the floor. We're just separating them into the parts that are pushing up and the parts that are pushing tangential to the floor. The part that opposes our motion as a part to opposing our going down or falling. Okay? So they're coming from the same place. I want to emphasize that. There's not like there's more molecules here. But on a microscopic level, they're all locked into place. If these were perfectly smooth, would you have any friction? No. So smooth surfaces tend to have very little friction. The rougher the surface, usually the higher the amount of friction. And so that's what he's trying to say in here. You're going to get some friction because of that roughness between them. And you can polish it smoother and smoother and smoother, but still it's always going to have some roughness to it. So you're always going to have some amount of friction. Could be less and less and less, and you could even, fill it up with a lubricant or something so it slides even better, but you're always going to get some amount. And so that's what he's saying. He goes, it pushes back. Now, I don't know if you've ever pushed on an object, but if you push a little bit, it doesn't move. And if you push just a little bit more, it still may not move. So what are you really saying at that point? Aren't you saying that the more you push, the friction is pushing back? Because what does the net force have to be if it's not going to move? 0. And your author does a good job of plotting some data here. He says, look, the static friction is kind of interesting here. The static friction is when you push with a force F, it will push back with a force that is exactly equal. We'll call it static friction. But how do I know it has to be exactly equal? Because the net force has to come out to be 0. In other words, if I push with 1 Newton and it doesn't move, that tells me it pushes back with 1 Newton. If I push with 2 and it doesn't move, then it means it's pushing back with 2. And then 3, and then 4. And so what we call the static region is really an inequality. And I think that's what makes our math kind of hard. I cannot tell you the static friction is equal to something. The static friction is a variable. It could be as low as 0 if you don't push, or as high as some maximum if you push up to some point. Now, at some point, wouldn't you agree it can't push back anymore? At some point, where the rough edges are locked into place, when you push more, they kind of break free. So there's a maximum. And that's what this is trying to say. There is a maximum. But there is a variation in between. Whereas, look at the next step. The next step says, what happens once they break free? Well, this is then what they call the kinetic region. And interesting enough, once they break free, it's kind of like they clip the tops of those rough edges off. Clip. And then they just slide, like a bunch of knuckles sliding over each other. They don't get locked into place. So did you notice something about the amount of friction? Didn't it lower? Once you started moving. And so there's 2 things I want you to notice about this. One is, it dropped down to a lower value. 2, no matter how much I push, the kinetic friction's about the same. And so I can write it as an equality.
Is that because of the inertia?
Well, no, it has to do with the molecules rubbing. And you can kind of imagine that if you're pushing slow, but moving, they kind of fall into place and they fall a little deeper than if you're pushing fast. If you're pushing fast, they don't fall as deep, but then they go and hit more hills. So you have less or more hills depending on your speed, but then they fall deeper versus the speed. So interesting enough, it comes out, and it's not perfect. It's just roughly the same. And so the kinetic friction is where we start with our problems because it's the easiest one. It is an equal to. It has nothing to do with how fast you're going, and it has nothing to do with what you're pushing. It is just equal, period. And you're going to appreciate that, believe me, because static friction is not that simple. Static friction depends on how much you are pushing. And air friction really is tough, which is why we don't do it this chapter. We do it next chapter. But it varies. So we're trying to start with some friction, but the easiest case of friction. Okay? And so these are our two frictions. Now, if you'll notice, he gave an equation here. He said the static friction, he says kinetic friction, as well as the maximum for the static friction, depends on this little coefficient in front. And he calls it the coefficient of friction. One is the kinetic. I'll just put it here as the coefficient of friction. This one is the kinetic. The other one would be static. But those numbers, I think you might be able to realize, has something to do with how when the material is made. Is it a well-polished surface? Or is it a rough surface? Is it made out of rubber? Or is it made out of concrete? Which is it? When you open up your book, you'll see he lists a whole set of them. He'll say, here is the coefficient for polished aluminum on aluminum, polished steel on aluminum, rough asphalt on rubber. You can probably guess where that one's going to come into play. Car going down the road. Concrete on rubber. Again, car, road, but concrete instead of asphalt. Waxed wood on ice. Skis. Okay, so the list goes on, what you'll see there. But he's given you a big table that you will need as you do the homework problems. You will need to know how much friction there is. And in order to do that, you need to know what materials he has. And he goes on to list, I think, Teflon and whatever the material is in your joints. Well, not the cartilage, the lubricating stuff. You'll see it in there. I forget what it's called too. It's a good thing it's not a biology class. But and so he lists that. What's the friction involved?
How would rubber work? How is it friction on rubber? Is it how?
Well, rubber is flexible, so it tends to take a grab, and then you see where these dents go in here. If you put rubber on something that had a coarse edge like that, the rubber changes its shape and sinks into the hills and valleys and kind of like fills in and kind of grabs the whole surface. Whereas steel on steel, there's a lot of parts that aren't touching. And so steel sliding on steel works much better than rubber sliding on that same steel. Or steel on asphalt compared to rubber on asphalt. Because that rubber gives and sinks in, if you will.
Which if that relates to gas,
Oh, yeah. Yeah, and so a gasket, the same idea, but of course, in that case, you're not trying to make friction, you're trying to seal it up so that, fluids don't leak out. Right. Okay, fair enough with the friction? All right, well, one more, and then maybe we'll start into some examples, and we'll have to carry this over till Wednesday. But I think you're in a good position then to do all these problems. A good one is, say, maybe I'll do this one. Here would be a pretty good and advanced problem. I've got two objects. The first one is kind of a square, or maybe I could call it cube because it's probably three-dimensional here. All right, so it's M1, and another a sphere, M2. One is sitting on the table. The other one is hooked with some kind of rope or cable over the side. It looks like over here we've got somebody or something pulling with a force capital F at some angle theta, right? seems to pull it with an acceleration of A. Could you write out the free body diagrams for this? What forces are on, say, the sphere? Aren't there just two? Right? The tension in the rope and gravity. How about this one? Okay, so there would be the force from this person's hand here. There should be a normal force from this table. There should be a gravitational force. And there should be some friction. Kinetic or static?
Well, it depends on.
So if it's sliding, it's kinetic. What does that say right there? That it is sliding, it is accelerating. So it would be kinetic. So let's see what the free body diagrams the author has here. He says, okay, well, let's look at that. He starts off with this one. Whoop, that's pretty small. This one here. He said, yeah, there's the free body diagram of number 2. How come he drew the T bigger than the M2G? Because what?
It's accelerating up.
Yeah, which one's going to be bigger, and how do I know? That T's got to be bigger than the MG2. Why? Remember, it was accelerating, right? Newton's second law right here. Newton's second law says, what if those two forces were equal? What would happen? No acceleration. It would just be it would just either be moving at the same speed or at rest there, right? But that's not what they showed. They showed it accelerating upward. So that tells me that it's got to be greater than that one. Okay? And so the tension is more than the weight of the object. If it was just equal to the weight, we wouldn't have an acceleration. So there's one free body diagram. The more interesting one is here. What is the free body diagram here? What are the forces in this one? Well, there's I think the easiest one, mg, right, pulling down. There is the normal force pushing up. There is the force from a hand. There's the kinetic friction. And there's the one nobody mentioned. Wasn't the rope tied to it also? Well, maybe some of you mentioned it. Okay, I didn't hear it, but okay, fair enough here. But there it is, that rope.
So does it matter where you draw the vectors? Because they're drawn for different places. Does it matter exactly where?
What do you mean draw where?
The vectors.
No, it doesn't matter where you draw them because we're just, after their size and direction.
Yeah.
So you can draw them anywhere you want. The author, though, I think the author has taken time to draw this one at its center for its center of mass, this one on its bottom edge because it's pulling back, this one right here because that's where the string is tied to. This one, he does the center. Doesn't really matter. Who knows why. But be careful here. What about these light blue ones? Yeah, those are the light blue ones. I want to make sure, the components of those ones. So the light blue ones is the author not trying to indicate another force. He's trying to say these are the components. And so as we go to solve a problem, we are going to have to break it down into its components to solve. Well, I think you guys got the right idea. Let me try one or even two in the 15 minutes we have left, and then we'll do more when you come back. But I want to make sure that hopefully you can get started here. The first one on my list is number 20. Number 20 shows this picture. It says, all right, let's take an object and hang it. Now, I've always wondered why the author picks a bag of cement to hang from the ceiling. But nonetheless, that's the problem. And I can't not think of any reason why we would be hanging a bag of cement from the ceiling. But that's what it says. It says, a bag of cement weighing 325 newtons hangs in equilibrium from 3 wires that are shown in the figure 20. 2 of the wires make an angle of theta 1 equals 60 degrees and theta 2 equals 25 degrees with the horizontal. Assuming that the system is equilibrium, find the tension in the strings T1, T2, and T3. Now, let's go through the first two and even the first four ideas that I was trying to say when you want to solve any one of these Newton's laws problem. Step one, do you have a good physical picture of what's going on? Do you see what's going on? We got a ceiling, we've got 3 ropes. Looks like the ropes come down and make an angle. In the diagram, he doesn't say the angle, but in the reading he does. I think he said 60 and something else here. 60 and 25. So this angle here is 60 degrees. This angle here is 25 degrees. The ropes then come together and have a bag of cement that has a weight of 325 newtons. He calls this the T1, he calls this the T2, he calls this the T3. I'll pause right there. Do you got a good physical picture of what's going on? Bag of cement, hanging. Now it says equilibrium, meaning what? Yeah, no acceleration. No movement either for that matter, but no acceleration here. All right, step 2, free body diagram. All right, so how shall we draw the free body diagram? All right, so I will draw just the bag of cement. What forces are on this bag of cement? Gravity? Okay, force of gravity. Anything else? Tension? Tension 1, 2, 3, 4, 5, 1?
4 because it's all those together.
It's a combination of 4.
1 T1 plus T2 plus T3.
So, is it T3? T1? Average of T1, T2, T3? T1 plus T2 plus T3? It's just T3. The only thing touching the bag is T3. Is T1 or T2 touching the bag? No, right? And that's why I picked this one, right? It shows really well, hopefully, you know, what you're going to make here. Now, don't get me wrong, doesn't T1 and T2 have something to do with this problem? Absolutely, but are they pulling on the bag? No, they pull on number 3, and then number 3 pulls on the bag. Fair enough? So just draw the forces that are on the bag. And so there's the free body diagram. Now let's write out the equations. All right, what are the equations? We haven't done this step yet. It says the sum of the forces equals mass times acceleration. Isn't that really 2 equations? Isn't that really the sum of the forces in the x direction and the sum of the forces in the y direction? Aren't these vectors? Well, good. So I want you to see that as I write out my first set of the equations. Now, of course, to do the x and y direction, I need a coordinate system. And why don't I just do the traditional, convenient coordinate system, x, y. Okay. I'll start with this one. How many forces do I have in the x direction? All right, 0. That was easy. All right, none. Kind of boring. And they have to equal to what? 0. Why? No acceleration. Okay, that works. 0 equals 0. Doesn't give me any information, so it's kind of a waste of time. But isn't it true? Add all the forces in the x direction. It's 0. What does it equal? 0 acceleration. Perfect. Let's try the vertical direction also. Add up all the forces in the vertical direction. What do you have? Well, pulling up is T3. Pulling down is the force of gravity. So I got 1 up, 1 down. Is that all the forces? Well, it depends what you call positive and negative. So I'm calling up positive in this little picture, so that's a positive force, that's a negative force. I could switch it around and, you know, same thing. But using the conventional one, one's positive, one's negative. Put together, what do they have to equal when you're together? 0, why? No acceleration, right. Acceleration in the y direction is 0. So what does that tell me about T3? T3 equals the Force due to gravity. What is the force due to gravity?
Negative 9.8.
That's the acceleration due to gravity, 9.8. What's the force due to gravity here? 325 newtons. They told me. They told me it weighs. Did I say weighs? 325 newtons. That is a force. They're telling me straight out. Okay? 325 newtons. There it is. So I have found at least one of the three. That's T3. 325 newtons. Okay? That is the force on T number 3. Okay? The force of gravity. Don't confuse that with the acceleration of gravity, 9.8. Now, you could have calculated it as mg, but we don't know m. So, of course, we could solve for m because we know its weight and we know g, but that would be force number 1. Now, I'm only 1/3 done with the problem. How do I get T1? Or T2?
Find the angle. Find that angle between and then do the component.
Okay, I hear people talking about x and y components, but it sounds like me you're adding up forces. So don't you have an object to add these forces up to? Yeah, so maybe you're selecting that as your object? All right, so give me another free body diagram. Right? This is T1. This is T2. T2. This is T3. And hopefully this illustrates, don't think there's only such thing as one free body diagram, right? There's a free body diagram for every object. It could be the monitor, the table, and the earth. We could have 3 free body diagrams. And in this case, I'm using a free body diagram for that knot, if you will, where they're all tied together. I know I'm going to need something that has a T1 and a T2 in it because it didn't show up when I did the free body diagram for the bag of cement. Now, same idea. Free body diagram. Write out the forces in the x direction. Set it equal to MA. Write out the forces in the y direction. Set it equal to MA. Okay? And so write out the equations, solve the equation. So again, those are your 4 steps. Step 1, good physical picture of what's going on. Step 2, free body diagram, or I should say diagrams. In this case, 2. Write out the equations. Solve the equations. Okay? So let me write out the equation. What would be this one? What would be the forces in the x direction? Remembering that this is 60 degrees and this is 25 degrees. Okay, so to get this x component, it would be magnitude times cosine of 60, and the direction would be negative. Did you catch that? Magnitude, component, direction again. Okay, so this is why we spend a lot of time in chapter 3, learning it more in chapter 4, really going to push it home here in chapter 5. Magnitude, component, direction. This is how much of T1 is in the x direction. It's in the negative. How about T2? T2 cosine 25 degrees, positive direction. Magnitude, component, direction. Okay, so I'm now adding all the forces in the x direction. I got the forces in the x from T1. I got the forces in the x from T2. How much forces in the x from T3? 0. So that is the sum of all the forces in the x direction. What does it have to equal?
0.
Yeah, why 0? No acceleration. 0. Right?
Should you write I hat, J hat, and K hat?
If you want to do I hats, we could write this in one equation, I hats and J hats. But this will be my equation for the I hats, and then right below it, I'm going to do an equation for J hats. I thought it would be a little clearer if I kept them separate for you. I don't care which way you want to do it. But I think at the beginning level, it's a good idea to not try to make one equation that has I hats and j hats, but to write them as two equations. Because I'm going to do the same thing here. Let's do the y direction. All right, so what are the forces in the y direction? How about start with T1 again? T1 sine 60 positive. Magnitude component direction. How about T2? Magnitude component direction. And then minus. Now here's the question for you. It's T3, but don't I know T3? So can I just put the 325? So it doesn't look like another something I don't know. I do know that one. 325. And what does that equal when I add it all up? 0 again. Why? Acceleration is 0. So you have two equations, two unknowns. So now I got a little bit of algebra to do. But that is step 3. Write out the equation. So I'll say it again. Step 1, got a good physical picture of what's going on. Step 2, write out the free body diagram. Good. Because once you get that free body diagram, it sets you up for step 3. Write out the equations. Okay? And so far, this is the hardest one we've seen. We'll see harder ones, don't worry. But so if you're kind of bored, they'll get much harder than this here. Okay, but this is right out. Now, step 4, solve it. And this is the part that I think you know how to do, but since we only have a minute or two and we can't start another one, I might as well solve it. Might as well solve this one. So I'm going to solve this one for T1. So T1 equals, and I guess I would have a T2 cosine of 25 degrees on one side of the equation, and divide it by cosine of 60 degrees. So that would be T1. And if I put T1 into this equation then, so T2 cosine 25 degrees over cosine of 60 degrees times sine of 60 degrees plus T2 sine of 25 degrees equals 325. When I bring this to the other side, I now have only one unknown. So T2 equals, and so I'm doing a lot of algebra here in one step. I don't encourage you to do it in one step, but we're at a time there. But I can factor out the T2 and divide. So this becomes cosine of 25 degrees times sine of 60 degrees over cosine of 60 degrees plus sine of 25 degrees. And there it is. And I just got to get out my calculator and punch it in, and I got the answer. Okay? Makes sense? And I bet you wouldn't have guessed that without writing out the equations. A lot of angles involved there. Cosine and sine. Well, I'll stop there. You work on them if you haven't already. It would be really good if you came back on Wednesday stuck somewhere and saying, I tried it. This is as far as I got. And I will do more examples, harder examples, and do some friction ones.